system. It consists of an extremely fuel-efficient 1.5 liter Atkinson petrol engine with a maximum engine thermal efficiency of 40.5%, which is very high, paired with two electric motors, one mainly used as a generator, the other one mainly used as a propulsion motor, with outputs of 80 kilowatt and 253 Newton meter for the propulsion motor. Some performance figures on the right side, but you can also have all these figures in your press kit. Now let me briefly explain the hybrid working principle. In general, this is basically the same working principle like the IMMD you can find in the CRV hybrid, but every component has been redesigned and made much more compact. So we have on the left side the petrol engine, which actually is connected to the generator and drives the generator. And on the right side, we have the propulsion motor, which is connected to the wheels. And the engine-driven generator creates the electric power and feeds this power directly to the propulsion motor. So this is already a significant difference to a range extender where normally everything goes through the battery. But while this is happening, the generator can still charge the battery, or the propulsion motor can receive assist power from the battery. And for the rest, there is no gearbox whatsoever. So there is no CVT or planetary gearbox included. That somehow minimizes the mechanical friction of the whole system. So this is a very important information. It's been misunderstood very often. Now that working principle I have just explained is what we call the hybrid drive mode in the middle. So you can see the engine-driven generator is feeding the propulsion motor directly with electric power. Now in some circumstances, this electric power can also come completely from the battery. So in that case, the combustion engine is switched off and we are running solely with electric power with zero emission. And in some other situation where the whole system detects that driving the wheels directly with the engine is the most efficient mode, then it actually closes the clutch and then the wheels are driven, or the car is driven by the engine directly, and this is the engine drive. Every mode is actually controlled and switched between autonomously in background so that the driver on one hand has no influence but also cannot feel the difference. Now such a complex system, engine driving the generator, feeding the propulsion motor in order to drive the wheels, seems to be quite complex. Why is such a system better in fuel efficiency than rather driving the wheels directly with the combustion engine? And if, let's say, a combustion engine would have the same efficiency in each operation point, yes, then that would be the best. But unfortunately, a combustion engine has very different efficiency depending on its operation point. And for that, let's have a quick look at such an engine efficiency map, which is plotted over engine speed and engine load. So this is a representative schematic graph of such an engine efficiency map. The lighter the color, the better the efficiency. So of course this light area, this is around 2000 RPM and 70% of engine load or engine torque. This is the sweet spot as we call it, and if you go away from that point, landing somewhere in the dark blue area, the difference in efficiency can easily be 50%. This means the engine would consume 50% more fuel just to produce the same amount of output. And that is the tricky part of an engine. So the target is always to come as close as possible to that sweet spot. And if we run through this engine efficiency map with a conventional car, with a petrol engine, with, let's say, a manual gearbox, then it will look like this on the left side. You can see the lines of the gears, and there are some representative area for urban driving, extra-urban driving, motorway driving, and you can already see that we're hardly hitting this sweet spot. Now, with the eHEV hybrid system, as I explained before, the engine and the wheels are mechanically disconnected by the clutch. This means we can operate the engine independently from wheel speed. So we can, most of the time, operate the engine around this sweet spot. And if that engine power is, for example, too high to actually drive the car, this means if the engine-driven generator is producing too much electric energy, then we just store it in the battery. And if the power is too low, then we give a little bit of assist from the battery so that nearly all the time the engine can be operated in this sweet spot. And this is basically the secret behind why the eHEV system can have a fuel efficiency benefit of 30 to 40% against conventional powertrain in real-world driving. This is an overview of a realistic drive data about the ratio of the different drive modes. So if we drive in urban area in speeds between 0 and 40 kilometers an hour, most of the time you run in electric drive, 86%. Even at extra urban, through country roads, between 40 and 80 kilometers an hour, more than half of the time you run in electric mode. And running in electric mode, this brings a benefit because that power stored in the battery, this was gained from, let's say, recuperated waste energy, deceleration energy. But also, this power has been charged into the battery by operating the engine in a very fuel-efficient area. On motorway, then the ratio of engine drive will increase more than 70%. And what is also very important to understand is if we go beyond 120 kilometers an hour on motorway up to top speed, the ratio of the hybrid mode will be nearly 100% because at higher speeds, it is still beneficial to run in hybrid mode rather than utilize the combustion engine for drive source. So this is also something which has been very often misunderstood. A lot of improvements have been done on the electric motor. The maximum speed of the motor has been increased, and therefore the new Jazz is reaching a top speed of 175 kilometers an hour, which is class leading amongst all the other electrified vehicles. Also, what we call the torque efficiency of the electric motor. This means how much torque you can extract from 1 ampere of current. This is also much higher than one of our main competitors on the market, 54%. Also, the motor losses. These include the copper losses, but also the iron losses. We call it the electromagnetic losses. That's also seen as heat losses that you can feel if the electric motor is becoming hot. This has also been optimized. And also the maximum torque level itself. Now, of course, this is a quite unfair comparison to compare the current Jazz with a combustion engine against the new Jazz, but just to see the difference in absolute figures, this is a 1.6 times higher torque level, even higher than a 1.5 liter turbo engine. So, and the good thing is the electric motor provides the torque right at the beginning.